Hey guys, it's Rue, and this is problem number 23 for chapter 3. So the problem says a man pushing a mop across the floor causes it to undergo two displacements. The first has a magnitude of 150 centimeters and makes an angle of 120 degrees with the positive x-axis. The resultant displacement has a magnitude of 140 centimeters and is directed at an angle for 35 degrees to the positive x-axis. Find the magnitude and direction of the second displacement. So the first thing that you should do is draw out the vectors that they give you. So the first vector represents the first displacement, so it's like the first movement that it makes. So the first one has a magnitude of 150 centimeters and makes an angle of 120 degrees with the positive x-axis. So you can draw this just as a 120 degree angle. So if you start from 0 and you go this way, like you know the unit circle, you know how to do an angle, and 120 degrees is like right here-ish. And then you just label it 150, and this is 120 degrees. And then you do your second vector, but the thing to note is that the second vector isn't actually the second movement or the second displacement. It's actually the resultant vector of the addition of the first displacement and the second displacement. So essentially you're kind of working backwards from the resultant vector and trying to find one of the other vectors that you added to this first one. So if you go ahead and draw the resultant vector, it's directed at an angle of 35 degrees and it has a magnitude of 140 centimeters. So if you just draw that from your origin, it's, I don't know, like around here, and you label that with your 140 centimeters, and this is about 35 degrees. So this can get really messy really quickly, but this is just to kind of set up the problem. So now that you have your initial vector, like your first displacement, and you have your resultant vector, you know that you have to find the second vector that you added to this one to get this one. So if you kind of work backwards, you know that the vector that you added to this one has to have its tail at the tip of the first vector, and it goes that way to meet the resultant vector. So if you just draw it like this, and we label it C. So now if you look, you have to find the magnitude and the direction of vector C, and this is easiest to do if you have a right triangle involved, but if you calculate this angle right here isn't actually right, so even though it kind of looks right in my picture. So what I did was I extended out both of the vectors, both the initial vector and the resultant vector, to create kind of a parallelogram shape that will actually give us more of a right angle to work with. But before I get into that, let's go ahead and find the x and y components of both of the given vectors. So starting with the resultant vector, if we go ahead and just draw it kind of independent from the axis, if you go ahead and label your vector with the magnitude here, and now we're looking, if you drop down, we're looking for the y components and the x components. Oh wow, this is completely tilted. Sorry guys, I'm a lefty, so my writing is all jacked up. So we're trying to find the x and the y components, and you do actually know this angle right here, which is 35 degrees. So knowing that, you can solve for x and y. So you just use your trig definitions. So let's start with solving for the y. The first thing you do is you take the sine of 35 is equal to opposite over hypotenuse, so that'll be y over 140. So when you solve for y, you're going to get somewhere around 80.3. And then if you go ahead and do the same thing, but you're solving for x, so for x, we're going to go ahead and use cosine, so you do adjacent over hypotenuse. So you do cosine of 35 is equal to x over 140, and if you plug that into your calculator, you'll find that x equals 114.68, or some rounded version of that. So now we're going to do the same thing for the first vector up here, the 150 centimeters vector. Now, again, we're trying to find the x and y components of this vector. So if you bring it down and kind of make it independent from the axes, here's the vector, and here you have your y component, and here you have your x component. And again, so you know that your magnitude is going to be 150 centimeters, and you also know what this angle right here equals. It's equal to 60, and the way that you find that is if you go back up to here, this whole angle is 120, and so you know if this entire angle is equal to 120, you know that this angle has to be equal to 60, because obviously this is 180, subtract 120 and you get 60. So going back to our right triangle, so again we're solving for the components of the first displacement vector. So you do the exact same thing using your trig definitions. So if you're solving for x, we can use cosine of 60 is equal to adjacent over hypotenuse, so you have x over 150. Solve for x with your calculator, and you are going to get x is equal to negative 75. And again, if you do the same thing to solve for y, you're going to have sine of 60 is equal to y over 150. So remember, you have sine is opposite over hypotenuse, so you have opposite over hypotenuse. And again, you plug it into your calculator and you'll get y is equal to 129.9. You can round here if you want, but I'm just going to leave it like that. And then what you're going to do is solve for the second vector. And the way that you do that is kind of what I talked about earlier, where you extend the original vectors and you kind of reposition them to create a kind of parallelogram. I'm going to go ahead and show you what I mean. And there's probably another way of doing this problem, but this is kind of how I did it, and it ended up with the right answer. So hopefully this helps. So what I did was I took the resultant vector and I redrew it. So this is not completely accurate visually, but whatever. So remember, this is 35 degrees, and this is your 140 centimeter resultant vector. And if you go over here and you look at your first displacement vector, I'm actually going to subtract this vector from your resultant vector. So remember, when you subtract vectors, you go ahead and flip the vector and then you do tip to tail again. So if the vector is facing this way, you're going to flip it and it's going to go the opposite direction. And when you subtract it, you have to move this vector and reposition it so it's tip to tail with the 140 centimeter vector. So what you're going to do now is take your vector. Remember, it kind of looked like this before, and you're going to take it, flip it, and reposition it. So when you reposition it and you flip it, the vector ends up looking somewhat like this. So remember, this is your 150 centimeters. The magnitude hasn't changed. It's just the direction has been changed. So now that you've flipped it, you can tell that you're subtracting the 150 centimeter vector from the resultant vector. And if you draw the vector that it's the answer for the subtraction problem, it's going to be this vector right here. And if this vector looks familiar to you, it should, because it's exactly the same vector that we're trying to solve for over here, except it's just a lot easier to deal with when it's in this form. So now that you see it like this, it's going to be just a case of simple vector subtraction. If we label the first displacement vector A and the resultant vector vector B, and the second displacement vector vector C, which is what we're solving for, we can go ahead and write out the subtraction problem, which is going to be vector B minus vector A is going to be equal to vector C. So you already have the x and y components of both vector A and vector B. So if you write that out, it's going to be, so you have vector B as 114.68, and the y component is 80.3. And you're subtracting vector A, which is going to be negative 75 for the x component, and a 129.9 for the y component, which is going to be equal to vector c. So focus, there you go. So then you just do simple subtraction, and you subtract your x components and you subtract your y components, and that's not hard to do. And you end up with a vector c is equal to 189.68, or some rounded version of that, and negative 48.9. So there's your resultant vector, but they are actually asking for the magnitude and the direction, so what you're going to have to do is figure out what the magnitude of the vector are. So here you have your components. If you take your vector c and you bring it down and you draw it independently of the axis, then you can go ahead and draw your x and y components. So here you have your x component of, or I'm sorry, your y component of negative 48.9, and here you have, oh, this is a terrible drawing, extend. Here you have your x component of 189.68. So again, pretend this is a straight line. It's a Pythagorean theorem, or a Pythagorean triangle. So you know what to do. And you have your degree right here, or your theta right there. So to find the magnitude, I'm going to go ahead and use the Pythagorean theorem. So everyone knows how to do this, but just to review, the magnitude of c is equal to the square root of the squares of the two legs of the triangle. So you have 189.68 squared, and you add that to negative 48.9 squared. And extending the square root sign all the way over, plug that into your calculator, and you're going to get a magnitude of 195.88, at least that's what I got, but again, if you round it differently beforehand, it'll be a couple decimal places different. So there's your magnitude. And the second thing you have to find is the direction. So direction is going to be in degrees. So you're solving for theta. So if you look at the two given legs that you have, you can use the tangent formula. So tangent of theta is equal to opposite over adjacent. So here's your opposite and there's your adjacent. So you plug that in, negative 48.9 over 189.68. And if you do inverse tangents with your calculator, so you'll be able to solve for theta. And theta you'll get negative 14.46 degrees. And the book actually does it, they don't give you negative degrees, they actually ask you to find it out of from 0 to 360 degrees. So obviously if you have negative degrees, you can just take that number, make it positive, and subtract it from 360 degrees. So when you look at this degree, or this angle, negative 14.46, it's the same as saying it's equal to 345.5 degrees, or when you round it, that's what you get. So if you write out your entire answer, you have your magnitude. So the second displacement has a magnitude of 195.88. This will be in centimeters, or in the direction of 345.5 degrees. And I don't remember whether this is the correct rounding that the book gives you, because it really does depend on where you round and how much you round, or what decimal place you round to. But that's basically it. Yeah.